Good morning to one and all. So far what we have seen, we have seen about how to design our FIR filter using windowing technique. So far we have seen about how to design a low pass filter, how to design a high pass filter. The next thing we have seen about how to design a band pass filter. So today we are going to see about how to design a band reject filter. Okay. So the thing is to be that the given problem is to be HD of e power j omega is equivalent to 1 for the omega which should be less than the limit which is given over here to be pi by 3 to 2 by 3 to pi by 3. Otherwise the value will be equivalent to 0. So let me know that the cutoff frequencies which is given as two different cutoff frequencies for the band reject filters. Omega C1 is equivalent to pi by 3 and omega C2 is equivalent to 2 pi by 3. So what are all the steps that we have to see over on it? So the first step we have to find out the filter coefficient. The second step we have to find out the rectangular window values. And third step, we have to find out the filter coefficient using the rectangular window. Fourth step, we have to find out the transfer function of the filter. On the fifth step, we have to find out the transfer function of the realizable filter. And the last step to be that we have to find out the real value and the imaginary values for the given filter. Okay. So now let me see the what about the filter coefficient. So we know the formula is to be that HD of n is equivalent to 1 by pi of n minus alpha sine of omega c1 of n minus alpha minus sine of omega c2 n minus alpha plus sine of n minus alpha into pi. Okay. So the thing is to be that we know that the cutoff frequency is to be pi by 3 and omega C2 is equivalent to 2 pi by 3. Okay. So let me replace the value to be n is equivalent to 0 because the value of n is equivalent to 11. The given problem for the windowing function to be n is equivalent to 11. So we will be finding off over the values from 0 to 5. So let me equate the value HD of 0, HD of 1, HD of 2, HD of 3, HD of 4 and HD of 5. Okay, so HD of 0, so when you are equating the value of 0, so obviously we can able to get the value of 0.667. And similarly, when we are replacing the value of 1, we can able to get the value to be equivalent to 0. And we know that it will be the mirroring value of mirroring value. So HD of 1 will be equivalent to HD of minus 1. HD of 2 is equivalent to we can able to get the value around 0.2757 and the value 3 the value would be equal to 0 and the 4 we can able to get a value minus 0.1378 at last the value of 5 is equal to 0. Okay, so these are all the filter coefficients by applying of a band reject filter formula. The next thing we have to find out using a rectangular window. So what the rectangular window, we know that rectangular window value will be equal to 1 for the limit varying from minus of m minus 1 by 2 to m minus 1 by 2, 0 for otherwise. So we'll have the value over here to be, we'll be having around over to be 1. So for the limit varying from minus 5 to 5. Okay. The next, we have to find out the filter coefficient for the windowing function. So h of n is nothing but an multiplication of windowing function with the filter coefficients of an undesired value. Okay. So W of n into HD of n. That is the meaning over here. So for 0 corresponding, we have to multiply it with the value of an WR of 0 with the value of HD of 0, WR of 1, HD of 1, WR of 2, HD of 2, WR of 3, HD of HR of 3, and then WR of 4, HRD of 4, and WR of 5, HRD of 5. So since we are using a rectangular, so we use the notation R. For handing and hamming, you can able to differentiate to be HAN or HAM, whatever it may be. Okay. So we can able to obtain the value to be 0.667, 0, 0.2757, 0, minus 0.1378, 0. Since the value of HD of 1, HD of 3, HD of 5 to be is equivalent to 0. Okay, what's the next step? The first step, we have to find out the transfer function of the filter. So H of is equivalent to H of 0 plus summation M is equivalent to minus 1 by 2. So H of n into Z power minus n plus Z power n. So I'll substitute all the values. We can able to get the value 0.667 plus 0.2757 Z power minus 1 plus 0.2757 Z power minus 2 minus 0.1378 Z power minus 3 and minus 0.2078 Z power minus 4. Okay. So now let me multiply in order to find the transfer function of the realizable filter. We have to use the formula of an Z power minus of m minus 1 by 2. Okay, so we'll be equating the value. So we can able to multiply value of z power minus 5. So the filter coefficients of the Cauchy filter, or we can able to obtain that h of 0, h of 10, h of 2, and h of 8, h of 4, and h of 6, the value will be equivalent to 0. Similarly, the value of 1 and 9 are to be the minus 0.1378, 3 and 7 to be the 0.2757, and 5 to be equivalent to 0.667. Okay. And the last step, we know that we are in need to find out the value of an real values and the imaginary values by using the formula h of e power j omega is equal to summation n is equal to 0 to m minus 1 by 2 a of n cos of omega n. So substitute the value of an a of 0, which of m minus 1 by 2. So we can able to get the value of an h of 5, so which is equal to 0.667. So for the value of a of n, that is starting from 1 to n to 5. So we can able to get the value of n 2h of m minus 1 by 2 minus 10. So 2h of 5 minus 10. So now find out the value of an a of 1, a of 2, a of 3, a of 4, and a of 5. So you can able to get the value around 0.55140 minus 0.2756 and 0. And the phase response can be able to find out the formula h of e power j omega is equivalent to 0.667 plus 0.5514 cos 2 omega minus 0.2756 cos 4 omega. Okay, so the table clearly indicates the magnitude and the phase value of the. So this is the way to design our FAR filter using our windowing function. Okay. Then and the next thing is to be that we have designed a high pass filter using a window with cutoff frequency 1.2 radian second and capital N is equivalent to 9. So here 1.2 radian cutoff frequency, that is to be the omega c, and we'll be having often, we'll make an assumption if t is equivalent to 1 second. So we'll be getting off an 1.2. So the impulse response by using the formula minus sine omega c n divided by pi. So 1 minus omega c by pi. So the value will be equivalent to 1.2. So 1 minus 1 by 2.5. So find the value of an hd of 0, hd of minus 1, hd of minus 2, minus 3, and minus 4, which is equivalent to the mirroring value of an 1, 2, 3, and 4. So we can able to get the value around 0.2966, 0.1075, 0.0469, 0.0719. Okay. So after that, since the value of an n is equivalent to 7, so we have to find the value of an Hamming window for the limit varying from minus 4 to 4. So we know the formula, which is equivalent to 0.54 plus 0.46 cos 2 pi n minus m minus 1 by 2 for the value limit over here. So 0 otherwise over there. So then after that, by substituting the value of n is equal to 0, 1, 2, 3, 4, we can able to obtain that 0.865, 0.5, 0.21, 0, and 8. Okay. Similarly, the next step, we all know that we have to find out the that is the filter coefficients of using windowing function. It is nothing but an h of n into hd of n into wh of n. So multiply both these values, we can able to obtain the value to be 0.618, 0.256, 0.058, 0.001, and 0.01 and 0.0057. Okay. So finally, the Cauchy filter coefficients, or that what we can able to get over there now. H of 0, H of minus 1, and H of minus 2, minus 3, and minus 4 are to be the value 0.618, 0.256, 0.058, 0.001, 0.0056. So this is the way to perform the design of an FAR filter for any FAR filter, either for a low pass or for a high pass or for a band pass and for your band stop. Okay. So we can do the homework around design an ideal differentiator with frequency response h of e power j omega is equivalent to j omega c pi for the limit varying from minus pi to pi using Hamming window. Okay, for n is equivalent to 8. Okay. The next thing we have to discuss about an frequency sampling method. So the procedure, what is the design procedure for FAR filter using a frequency sampling method? Okay, this is the one of the last. This is the last method that what we have to discuss in the unit 3. Okay. So FAR can be specified impulse response, which is given as an h of n is equivalent to 1 by n summation k is equal to 0 to n minus 1 h of k e power j 2 pi k n by n. Okay. So if you are taking the Fourier transform, that is h of k is equal to summation n is equal to 0 to m minus 1 h of n e power minus j 2 pi k n by n. So wherever this h of k they are to be given as an DFT samples, there is h of k. How will be obtaining h of k? the z value has to be replaced by e power j 2 pi k n by n. Okay. So summation n is equal to 0 to m minus n h of n z power minus n. Okay. Now let me frame, let me equate, these are to be the equation number 1, 2, 3, and 4. Let me substitute the value of 1 in the equation 4. So what we can able to obtain h of z is equal to summation n is equal to 0 to m minus 1, 1 by n, summation k is equal to 0 to m minus 1, h of k e power j 2 pi n k by n z power minus n. So if you are replacing z is equal to e power j omega, so what will happen now? H of j e power j omega is equivalent to h of z. So which is nothing but omega is equivalent to 2 pi by n. Okay. So this is about the design procedure using frequency sampling method. So what are the general steps? The first step, we have to draw the filter graph in FAR design using windowing function. Second step, we have to draw the unit circle and mark the points if k is equal to 0, 1 up to n minus 1. So if theta is equivalent to 360 degree divided by n into k, and then if you are replacing k is equivalent to 1, then the value theta is equal to 360 divided by n. Third step, we have to find out the h of z, replacing omega by 2 pi by n. That is hd of e power j omega is equivalent to e power minus j alpha omega or e power minus j n minus 1 by omega. For k is equal to 0 for the pass band values and for k is equal to stop band values. Okay. So in type 2 design, we can replace omega is equal to 2 pi j by n, k plus 1 by 2. Fourth step, we have to find out the value of an h of n. So this is will case have two different sequence, one if n is odd and one if n is even. So h of n is equivalent to 1 by n plus h of 0 plus sum of this value to real part of this value. And if n is equal to 0, 1 by n of h of 0 plus summation is equivalent to n by 2 minus 1 of 2 real part of h of k e power j 2 pi k by n. So the final thing is to be that we have to find the h of z. So these are all the steps which are behind over here in the case of an frequency sampling method. Okay. So let me discuss the how we can design the how we can design FAR filter using frequency sampling method in the next class. Thank you all.